Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 7 from the May-June 2023 International A-Level paper from Cambridge. This is paper 4, variant 1 of the 9709 mechanics syllabus. And the question here is about a car of mass 1,200 kilograms traveling along a straight horizontal road. Okay, so you got this car. There's the road. 1 second. There's a road, and here's the car. I'll draw it like a block. Okay. And the car has a mass of 1,200 kilograms. Okay. There's a driving force that's pulling the car along, which we don't know explicitly what it is. Okay. It says the power of the car's engine is constant and is, so that's a constant force, equal to 16. Well, that's not the force, that's the power, right? The driving force is related to the power. And there's a constant resistance to motion of 500 newtons. So the opposite direction you're going to have the resistance to motion acting. Those are the things we need. Well, we know we want to find the acceleration at the time. So we want to find A when it's moving at a speed of 20 meters per second. So it's not going at constant speed. Okay. Its acceleration and its speed is changing. We want to find what the acceleration is at the time when the speed was 20 meters per second. Okay, that's like at that particular point. All right, so now when we're dealing with power, okay, we have two equations that we can be dealing with. One is the driving force times the velocity, and the other one is that the power is equal to the work done divided by the time taken. Okay, so in this particular context here, in this particular question, what we need to know is the driving force. Okay, and the driving force is going to be given by power over velocity, because we have the power, okay, which is 16 kilowatts. That's 16,000 watts. We should write it in SI units, divided by the velocity that it's traveling at, which is 20 meters per second. So we can say the driving force is equal to 800 newtons. So we know that this is now 800 newtons. And the resistance to motion, we're told, is 500 newtons. So I don't even have to write that, are there? That's 500 newtons. So I know that this is at the point when it's going at 20 meters per second, we can say the resultant force is equal to its mass times its acceleration. Now the resultant force is, as it's going this way, I'm going to take that as positive. It's going to be D, which is 800, minus 500. That's the resultant force. And that's equal to the mass, which is 1,200, times acceleration. And that's what we're trying to find here. Okay, so that's going to be 300 over 1,200, which is a quarter. Okay, they cancel out. You're left with A equals 3 over 12. So A is equal to 0.25 meters per second squared. So that's the acceleration at the time or the point when the velocity is 20 meters per second. So that's part A. So the key for this is to know about this equation here. Power is driving force times velocity. Once you know that, you can work out what the driving force is, the resultant force is, and therefore the acceleration of the car at that time. Okay, so there's part A of question number 7. Now we're going to move on to part B. It says, assuming that the power and the resistance forces remain unchanged, find the steady speed at which the car can travel. So basically, this is a very common question. Very common question. Okay, and we know that the maximum speed is when the acceleration is 0. Okay, like for example, if you have a velocity time graph, the maximum velocity would be, if you have a graph like that, would be when the acceleration is equal to 0. Okay, the power and resistance forces remain unchanged, so the steady speed at which the car can travel. So when the acceleration is equal to 0, okay, that's when you're going to have a steady speed because it's still accelerating. So basically, when the driving force minus the resistance force is equal to 0, that's when you're going to have maximum acceleration. Okay, so the driving force and the resistance force, okay, remain unchanged. So the driving force is equal to, remember, the power is equal to the driving force times the velocity. Okay, so we can say that the driving force is going to be the power over the velocity. So we're going to have 16,000. Is it 16,000? Yep, divided by the velocity minus the resistance force, which is unchanged, which is 500. So the power has remained unchanged, the resistance force has remained unchanged, and we want the resultant force to be 0, because when it's going at its maximum speed, okay, that's when you're going to have acceleration equals 0. Maximum speed means acceleration equals 0, I should write. Okay, so the maximum speed is when acceleration is equal to 0. So we're going to have here 16,000 over v equals 500. So we can just rearrange this. The velocity is going to be 16,000 divided by 500. So it's going to be 160 divided by 5. So you have 160. Whoops, what happened to my calculator? 160 divided by 5, which gives us 32 meters per second. So that's the speed at which, okay, the car can travel when it is, that's the steady speed at which it can travel. Okay, when the acceleration is equal to 0, that's going to be when it's a steady speed. Steady speed means no acceleration, basically. Okay, so there's your answer to part B of this question. Now we're going to go on to part C. It says a car comes to the bottom of a straight hill of length 316 meters. Inclined at an angle to the horizontal of inverse sine of 1/60, the power remains constant at 16 kilowatts, but the magnitude of the resistant force is no longer constant and changes such that the work done against resistance force in ascending the hill is 128,400 joules. The time taken to ascend the hill is 15 seconds. Given that the car is traveling at a speed of 20 meters per second at the bottom of the hill, find its speed at the top of the hill. So let's make a diagram. Always in mechanics questions, making a diagram really helps to sort things out. So we're going to have a diagram that's representing the hill. You have the particle or the car going up the hill. Okay. So it's going up the hill now, and it's trying to make that straight. Okay, it's 1,200 kilograms, of course, same weight. Okay. At the bottom of the hill, it's moving at 20 meters per second. We want to find its speed at the top of the hill, okay, which we're going to call v. All right, that's what we have to find here. Now, we know a few things about this situation. We know that the angle here, the sine of the angle is 1/60. I'll just call this theta for now. And we can say sine of theta is equal to 1/60. Inverse sine of the angle is 160. That's the sine of theta is 1/60. All right. We know that the length of the, this distance that's traveled along the hill, okay, from there to there, that total distance there is how long? 316 meters. 316 meters. And one of the things we would need to know is how high this, how much it's risen by in this. That's what we're going to know. We need to know that. So I'll just put that over there. So I need to know this height here. This is the height through which is written vertically. That will help us in this question. We're going to deal with work, energy, and power. We're going to work here with it's called the work energy principle. Okay. So now, the other thing I'm going to do is I'm going to call this the point of zero potential energy. Okay, and then, we're going to deal with energy here. So what else do we need to know? Okay, so we know that the resistance, okay, in ascending the hill is 128,400 joules, and the time taken to ascend the hill is 15 seconds. Now, we know that the power is remaining at 16 kilowatts. So the power is 16 kilowatts. And I know that power is equal to work done over time. Right, so that's going to help us, I think, this question. So what I'm going to do here is I'm going to use the work energy principle, which basically states that the kinetic energy at the start, which I'm going to call A, that's the start point, and that's the end point, I'm going to call it B. So kinetic energy at the start plus the potential energy at the start, which is A, plus the work that goes into the system is equal to the kinetic energy at the end, which is at B in this case, plus the potential energy at B, plus the work that's coming out of the system. Okay, so the kinetic energy at the start is, now what we should know, what we should understand is kinetic energy is given by the formula a half times m times v squared, kinetic energy. And potential energy is to do with the gravitational potential energy. That's given by m times g times h, where h is the displacement from our zero position. Right? So for at A, we know that it's going at this speed here. This is velocity at A. Velocity of B is what we have to find. Call that B. Right? So a half times the mass, which is 1,200, times VA, which we know, times VA, which we know is 20 squared. Okay, half mv squared, plus the potential energy at A, which is 0, because we've defined this as a 0 level, so the displacement is 0, so m times g times 0, that's going to be 0, plus the work that goes into the system. Now the work that goes into the system, is basically determined by the power of the system. So the power is not the work, the power is the rate of the work being applied. So if I want to find the work done, I've got to take the power and I've got to multiply it by the time for which the power was acting. That will give me how much work was done, all right, in that time. So you have 16 kilowatts, 16,000. Let me just write that properly. 16,000 times the time. You have 16,000 times the time for which it's acting, which is 15 seconds. And that should give us our work in. That's the work done in pulling this up the slope. So 16,000 times 15 is 240,000. So that's 240,000 joules. That's the work in. So this is going to be 240,000 joules. Now, the kinetic energy at B is going to be a half times 1200 m times what we have to find, VB squared. Find what VB is, right? Plus the potential energy. Now we need to know what this height is. So I can use the fact that this is a right angle triangle. I know that the sine of the angle theta is equal to h over 316. Therefore, h is equal to 316 times the sine of theta, which is 316 over 60, right? So h is 316 over 60. Why? Because sine is opposite over hypotenuse. And we know that sine theta is 1 over 60, as I told us in the question. So if I just now just do that, 316 over 60, what does that give us? It gives us 5.266. I'll just leave it at 316 over 60 for now. Okay, so that we have exact values until the end. So that's going to be 316 over 60. So m, which is 1200, times g, which is 10, times 316 over 60. Okay, 300 what? 300, 79 over 15. I'll keep it at 79 over 15. That's better. 79 over 15, simplified a bit, but not writing it as a decimal. 79 over 15. Okay, is that correct? Yep. Okay, so that is the potential energy at B plus the work out. Now the work out is the work done against the resistance forces, the things that slow it down. So the work in are the things that like pull it or push it, make it move up. Okay, it's helping it to move along. And the work out are the things that slow it down, like friction or resistance to motion or something like here. The resistance force against the motion is 128,400. So that goes in the work out place, 128,400. Is that right? Yeah. So now we have to find what this is. Okay, we have to find what this is. So we're going to have here, let me just simplify this about, that's going to be 600 times, and that's going to be 400. That's going to be 24 and 4 zeros. So 240,000 plus another 240,000, that's already given, equals, that's going to be 600 times VB squared plus, let me just work that out. You have 17 over 15 times 10 times 1200. Okay, that gives me 63,200, 63,200 plus 128,400. So let's add these together. 128,400. Okay, so that gives me 191,600 plus 600 VB squared equals, this is going to be 480,000. It's just double basically. So we're going to have 480,000 minus 191,600 over 600, and that's going to be equal to VB squared. So let's work out this. We'll have 480,000 minus the last answer, which was that 191,600, divided by 600. Okay, that gives us 1,442 over 3. 1,442 over 3 VB squared. Therefore, the velocity at B is going to be given by the square root of this answer, which is 21.924. 21.924. So we say the velocity of B to 3SF is 21.9 meters per second. Okay, so that's how we deal with such questions as this to do with work, energy, and power. Okay, so this is a very, very important equation here called the work energy principle. And, you know, it works in any situation, whether there are external forces. Here, there's external forces acting, which are the power that's driving or pulling this up. So the energy caused by that is going to be power equals work done equals power times time. That's how we found that. And the work coming out is the work done against the resistance during its motion, which they told us already is this number. So those are what we have to add into this equation. The kinetic energy at the start plus the potential energy at the start plus the work in will be the same value as the kinetic energy at the end plus the potential energy at the end plus the work that came out of the system. And that will help you to answer all type of questions like this. So I hope that was clear. Other questions from this particular paper can be found in the playlist that will appear in this section over here at the end of this video. You can also watch other questions dealing with work, energy, and power by looking at this video here. You can subscribe to my channel by clicking on this link, and the video that's linked up here will take you to a video which tells you how to use my channel efficiently to find what you're looking for. Thank you for watching, and see you soon.